Let us start. Okay?
Yeah.
Okay, we were discussing the other day corner maps. How to simplify using corner maps, Boolean functions. We talked about 4 variable maps, 3 variable maps and 4 variable maps. We talked about sum of products, product of sums, how to simplify using zeros, then we get minimum product of sum, maximum product of sum, and then we minimum sum of products using ones. We also told you how to change from one to the other using De Morgan's theorem. You can also directly, once you have a map, you can read once, then you get sum of products. If you read zeros, you get f bar, complement of f, then you can simplify it and then take De Morgan's, or you can directly read zeros and get the product of some expression. All that we saw depending on the type of gates we have. Sum of products will have AND gates followed by OR gate. Product of sum will have OR gate followed by AND gate. And today we will talk about a couple of things. One is called don't care states. Sometimes when you have an expression of 3 variables, 4 variables, 5 variables, some combinations do not occur. A typical example is, supposing you want to do a BCD, binary coded decimal. You have 4 bits, B0, B1, B2, B3, they only take the values from 0 to 9. But with 4 bits I can have 16 combinations, out of which the last 6 combinations 10, 11, 12, 13, 14, 15 are not used. So when you write the truth table, I will have all the 16 combinations, but we are interested only in the first 10, 0 to 9. Starting from 11 to 16, we do not get that combination at all, because we will only after 9 we go to 1 0, which is 10. Such a possibility is called a don't care condition. For example, if you have BCD combination, 4 variables ABCD corresponding to F, we write 0 0 0 0 through 1 0 0 1, this is 0 to 9. So we will have zeros and ones, etc. And then 1 0 1 0 to 1 1 1 1, these 6 combinations do not occur in my requirement, because I am dealing with BCD numbers. We will see this later on when we do a display. See, all these digital circuits today, you find displays. You go to bank, the teller has a display. Go to railway station, that is the display. So the displays, they can't do hexadecimal display. We do not understand it. It has to be decimal display, 0 to 9. But then we have 4 combinations, 4 variables, 16 combinations. The last 6 do not occur. These are called don't care conditions, because they do not appear. Don't care. Does not mean that we do not care. These inputs do not occur in our application for a specific thing. So this is very useful, because whenever a don't care occurs, this is not going to occur in practice, but this can be treated as a 1 or 0 to simplify the expression. I will give a simple example using 3 variables. These things we will see later when you go to combinational circuits. We will talk about many circuits, adders, subtractors, we will talk about multiplexers, we will talk about displays. At that time we will see this again, but just to illustrate the point, I will give a very simple circuit with only 3 variables. A, B, C as input and F is output, as we have been seeing. Out of which, let us say this is 1, first combination as an output 1, second combination does not occur. Do not ask me why, some reason. For some reason this combination of inputs do not occur. There is a combination of A0, B0, C1 does not occur in your circuit. Maybe different reasons that C is not available when both are 0, C is not 1. So we put an X here, X, D or X, X for don't care, or sometimes people put D as don't care, does not matter what you put. Then we have 0, 1, 0 is 0, 0, 1, 1 is 1, this is 0, this is 0, this is 1, this is don't care, this one. So I have two combinations 0, 0, 1 and 1, 1, 0. By the way, these are complements. This is 0, 0, 1, this is 1, 1, 0. These two combinations do not occur. When these do not occur, I do not know what output should be. Output can be 0, output can be 1, does not matter to me because it is not going to occur at all. When it is not going to occur, how does it matter what the output should be? So I put a don't care or X. So when you draw the corner map for this, this is 1, this is don't care, this is 0, I do not have to plot, I only plot ones or zeros, not all, not both, because the circuit the map gets cluttered. We have to either read ones to get sum of products or read zeros to get product of sums. There is no need to put everything. So I will put only ones and don't cares. This is 0, 1, don't care, 0, 1, 0, 0, don't care, 1. Now, how do we read this map? Now this don't care can be treated as a 1 or a 0. It is not going to occur. If it is not going to occur, it does not matter if it is going to be a 0 or a 1. We will use it to our advantage. We will use it to simplify the circuit. So for example, this one I will combine this don't care. If I do not have this don't care, I will have this one as a separate one. It will be A bar, B bar, C bar. Now because this don't care I am treating as a 1, I read this as A bar, B bar. So I have already reduced one variable. A bar, B bar, C bar it would have been, but now it is A bar, B bar. Now this don't care I do not have to see, you do not have to combine all the don't cares. Use only those which are required to simplify the logic. This don't care does not help in simplifying logic. So this is BC. So my F is A bar, B bar, BC. So this is the idea of a don't care state. Don't care state can be used as a 1 or a 0 depending on whether it is going to simplify the logic or not. Do not include all the don't cares because it is going to unnecessarily, now if I have to include this don't care, I will have to put one more here which is AB, which is not required because this don't care need not be, because this one is already included. I have already covered this one, so I do not have to do this, so this is not required. Whereas this don't care is included to reduce this from A bar, B bar, C bar to A bar, B bar. That is the advantage. Okay. So, this we will see more and more later on when you do decimal arithmetic using hexadecimal numbers. BCD, binary coded decimal, which is only in 10 digits 0 to 9, whereas there are 16 combinations using 4 bits. So, out of this last 6 bits, last 6 combinations will have no use, and those conditions will be put as don't care. So, also will be used in counters. When you do a counter, you want to count only up to a certain value, but then we have more bits. So, the last few states are not going to occur in the counter, put them as don't cares. So, the don't care condition being used as a 1 will reduce the logic. At the same time, we should make sure that you do not have to include all don't cares, because trying to include all the don't cares will result in a logic more than what we need. So, don't care is used to simplify the logic wherever possible. That is what I want to tell you. We talked about 4 variables, 3 variables. We talked about sum of products, product of sums. We talked about reducing using ones, reducing using zeros, and I also talked about 5 variables, 6 variables. I will only give one example using 5 variables. How do you have, say 4 variables, we have a nice map, 16 cells, 2 dimensional. 5 variables will have 32 cells. How do you draw a 32 cell? So, I will give you one example of that before we moving on. So, let me have a 5 variable map. Using 4 variables, using 5 variables, A, B, C, D, E. We will have 0 to 31, 32 combinations. Which of these combinations are 1, which of the combinations are 0, or can be reduced, can be given easily by an equation, sigma min terms 0, 1, 4, 5, 13, 15, 20, 21, 22, 23, 24, 26, 28, 30, 31. 0 to 31, 32 combinations, out of which these combinations have an output 1 in the truth table, other combinations have output 0. How do I represent it using a map? I need 5 variables, that means I need 32 cells. Nicely you can draw up to 4, 4 times 4 is 16. So, what we do is, in this case, we draw 2 maps, each 16 bits, 16 cells. The first 16 combinations will have A equals 0, because we are going to start with 0, 0, 0, 0, 0 and go on to 1, 1, 1, 1, 1. Out of these first 16 combinations will have 0 as, this is A, B, C, D, E, A, B, C, first 16 combination will be A is equal to 0, second 16 combination will be A is equal to 1. So, I divide this map into 2 halves. First half will have A is equal to 0, second half will be A is equal to 1. So, out of this The other 4 variables B, C, D, E we will put here. Now 0 to 15 min terms here, 16 to 31 min terms here. So first 16 up to this will be A is equal to 0 map, beyond this will be A is equal to 1 map. So this is 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Rest of them are zeros. 0, 1, 2, 3. If you want, you can help. If you want help, you can put a 0, 1, 2 like that. I don't want to do that. It's only unnecessarily cluttering the map. We know that now, by now. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, this is 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. How do I read this? You can independently read this. All you have to do is to add A0, A bar. For example, I can have a grouping of these 4 ones. These 4 ones will have B bar, D bar. I will call this 1. Prime implicant. Prime implicant 1 will be B bar, D bar, but I will have to add A bar into this because everything in this map, everything in this half of the map will be A is equal to 0, A bar. Now, these 2 I will leave now for now. I had this. Did I make a mistake here? Let me see. This is, what did I say here? 30. I think these ones should come here. This is 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Just to explain this a little more, I am going to change this one from here to here. That means I am going to make this 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Instead of 28, I am going to make it 29. Just to illustrate a point. I am just changing it momentarily to 29 instead of 28 because that way I can prove a simple point here. Now, these 4 ones make a group. This I can call prime implicant 2. 2 would be anything with this map will be A is equal to 1. A, B bar C. this map, the point here is identical to this same position here, I have this. This and these are identical positions, except in this case it is A is equal to 0, this case A is equal to 1. So, I am going to combine these two and call them prime implicant 3. So, in this case A is 0 for one half, A is equal to 1 is the other half. So, I do not have to put A now, it is now D bar, no, it is now BCE, BCE, combining A is equal to 0 and A is equal to 1. Now, there are two more left out. This one, this is 4, prime implicant 4 would be A, because in this half A is 1, B, D, E, A, B, D, E bar. And this can be combined to make it 5, prime implicant 5. Prime implicant 5 would be again A 1, this is E bar, B C bar, B bar, B C bar, E bar. So, now my final F will be sum of all these prime implicants, 1 plus 2 plus 3 plus 4 plus 5. The point I am trying to make is very simple. 32 cells cannot be put as one map. You can put it. Some books put some diagonal line, put here and here like that. You can see some books in which they will put this. Put a line here. They will put 0 here, 1 here, 0, 1, 0, 1, 0, 1. That is clear. That is confusing. This is better. I divide into two groups. A is equal to 0 group, first 16, 0 to 15, second 16, 15 to 16 to 31. A is equal to 0 group, A is equal to 1 group. Independently read them. Whenever you read this, you always have to add A bar. Whenever you read this, you have to put A is equal to 1, but if they occur in both places at the same place, both maps in the same place, then A is equal to 0 and A is equal to 1 gets knocked off. So, this becomes this. So, this is what I wanted to say. This and this make as BCE, A bar, A both gone. Otherwise, this is simple. This is, we know how to read this, you know how to read this, you know how to read this, you know how to read this. This is different because of these two. Only thing I earlier put 28, then I realized that 29 if I put I have the same positions. So, I changed it 29. Now, I can do 6 also like this. For 6 variables, I can do 4 maps. A bar B bar, A bar B, A B bar, A B. then I can independently read them, or if there is common things I can combine them. It can be done, but after that it gets a little difficult. With 7 variables, 8 variables. That is why we go for the computerized methods. One is Boolean algebra. In Boolean algebra, very simple rules are there, but you should know what to apply. The given function, what identity should be applied to simplify it, that has to strike. If you don't get that, you will not get the minimum expression. Second thing about Boolean algebra, you keep on applying Boolean rules, it gets reduced, you won't know where to stop. Second is the map method, up to 5 variables comfortable, 6 variables okay, but 5 variables comfortable. You look at the map, combine the ones, that gives you the simplest possible expression, no questions asked. You cannot reduce it further. Of course, it is in sum of products or product of some form. If you have other gates like NAND gate, NOR gate, exclusive OR gate, you can't use this. After you do this, you have to do some simplification to go to the NAND form, NOR form, etc. And the third method, which is more than 6 variables or 7 variables, you give computerized reduction. There you don't have to know the rules, there is an algorithm, there is a program, you apply this min terms which are available. For example, you feed 0, 1, 4, 5, 13, 15, 20, 21, 22, 23, 24, 25, 29, 30, 31, and it comes up with this result. That is called reduction by computerized method. There are several methods. One is called Quine-McCluskey, so many other methods. That is all very standard. Nowadays, with lot of designs involving huge number of variables, large circuits like microprocessors, you don't use this type of things, you use that computerized methods. That is not the scope of this course. You will learn these things later on in your advanced course in digital. Any questions? Anybody has a question? Please raise your hand. No questions? We will discuss about arithmetic circuits, adders, subtractors. We talked about multiplexers. We will do all that. Before that, I want to tell you something briefly about using NAND gates and NOR gates. I told you, if you remember, NAND and NOR are called universal gates. That means any circuit, any logic function you can have in any form, it should be able to reduce it to NAND gate, NOR gate combinations. Why do we do that? Because, as I said, when you do a IC design, it is easy to do one type of gate all through. That makes the circuit more efficient. And NAND and NOR are easy to defabricate compared to other circuits like other gates like AND, OR, exclusive OR, etc. So NAND and NOR combinations are very useful. We will look at some simple circuits to see whether we can convert them into NAND NOR combinations. I have a circuit. Suppose I have a circuit. A, B, C, A, B bar, C bar, A bar, C, dV feeding into this F. 3 OR gates feeding into an AND gate, each of them 3 inputs, 3 into OR gates, 3 of them feeding into an AND gate which is also 3 inputs. So, what is the output here? This is A or B or C, this is A or B bar or C bar, and this F would be and suppose I say use only NOR gates. The same logic I want, same output I want, use only NOR gates. Very simple, because I convert each of these NOR gates, OR gates into NOR gates by putting a bubble. This becomes an OR, AND gate with inverted inputs, also an OR gate. AND gate, OR gate with inverted output becomes an OR gate, AND gate with inverted input becomes an OR gate. So, this bubble I put another bubble to cancel, this bubble. So, this bubble and this bubble get cancelled, this bubble and this bubble get cancelled. So, there is no change in the circuit, there is no change. The circuit is going to look like this. As simple as this, not always. This is a very simple example. Two possibilities. One possibility is they may ask you further restriction, use only 2 input gates. These are 3 input gates, 3 input OR, NOR, 3 input NOR, 3 input NOR, 3 input NOR. The question can be use only 2 input. We will see one such circuit. Before that, I will give you another example. Supposing I have a circuit like this. This is example 1. Second example. AND gate feeding into another AND gate, feeding into an OR gate, feeding into another OR gate. This is my F, A, B bar, C, D, E. What is F? F is A and B bar and C or D or D or E. This is my F. This is AND followed by another AND followed by an OR followed by an OR. So, this bracket has no meaning because this is D or E. So, this will be simply AB bar. Supposing I say use only NAND gates. Get this circuit implemented. Now it has 2 AND gates and 2 OR gates, all 2 inputs. I want you to do this using only NAND gate. Now, I can easily combine this, make it into an OR gate, I mean NAND gate. Suppose I convert the NAND gate, no problem. But then this input, this inverted input, this is non-inverted input. In order to make it an inverted input, I put an inverter in between. An inverter can be also put using we know that the NAND gate with both inputs connected is also an inverter. This inverter is nothing but a NAND gate with both the inputs tied together. So, this is also a NAND gate only, even though I put it as an inverter symbol, in reality it can be a NAND gate. No problem. So, this NAND gate has been taken into account, this become alright. Now, I put this also as a NAND gate. If I make it the NAND gate, I get an inverter output here. That means, if I make this OR gate with 2 inputs inverted, to get an OR gate with 2 inputs inverted, that becomes a NAND gate. So, I can make it into an inverted, but this does not get that inverter. If you want to make an inversion here, I should make it as a D bar. I should get an inverter. D has to be inverted. This D gets inverted, then this becomes a NAND gate. Then I can go to the next one. Because this is an inverter, this is a NAND gate, this is a NAND gate, I can make this a NAND gate by putting an E bar here. That means if I want to redraw the circuit now, it becomes a B bar C then one more NAND gate whose input is inverted again. This should be D bar. So, this is D, this is D bar, and this will go into another gate with inverted. This is F. So, this is A B bar, C is not affected, D gets affected by the inverter, becomes D bar, and E gets affected by an inverter because it becomes E bar. This is the equivalent of using only 2 input NAND gates. This is very useful exercise because, as I said, many times you are asked to do a circuit, you simplify it and or invert form using this type of logic, but use only AND gates, NAND gates. If it is only NAND gates or NOR gates, you simply make OR into NOR and into NAND with put inverters appropriately. But the problem comes when you are asked to do only 2 input gates, then I should know how to add a extra inverter wherever required. We will do one more of this. Any questions? How do you make a 3 input OR gate into an OR gate? So, we can have following combinations. We can have AND OR invert, or AND invert, NAND NOR, NAND NAND, NOR NOR, NAND NOR, NOR NAND. Any of these possibilities is possible by properly applying the. Do not change the logic. F should not change, and you should use minimum number of gates. Try to cancel whenever possible. With that example, I will give you one. Convert using NOR gates. OR gate, AND gate, OR gate, another OR gate, and an AND gate. This is A B bar, C, D, E, F, G. So, F is A B bar, A R B bar. A R B bar, and C or D then you have E or F, this and E or F and G. This is the total function. and this is f. Actually, I have used f here, so I will call it x or z because f is there here also. Use only NOR gates to convert this, but no restriction on number of inputs. I can have 2 inputs, 3 inputs, 4 inputs, whatever you want. This will be my last example on this. We will have the next assignment, we will have this, more and more of this. We have, first I will convert into NOR, use only NOR. I have already written that using NOR. So this OR has become an OR, which means there is an extra inversion here. I should cancel this by another inversion here, right. So that inversion can come from a input NOR gate, but C cannot be, this is inverted. For a NOR gate, both inputs should be inverted. So this should be inverted, which means this should be inverted. This becomes C bar. That way these two inverters get cancelled. This bubble here gets cancelled with this bubble here, but this bubble is not there, so I have to put an extra inverter here. Okay. Then next stage is OR gate. I can put an OR gate in that, no problem, with a D. Similarly, E and F I can put an inverter, NOR gate. No inversion required here, no inversion required here, no inversion because these two are NOR gates. But now this has to feed into a NOR gate with 3 inputs, this has to feed into an OR gate. This inverter and this inverter gets cancelled. But I have extra input G which needs to be inverted, so put a G bar. So this is my Z, the output. Now I will have A B bar, NOR, C bar, NOR, D, NOR, E and F, NOR, G bar. This is my output Z, Z. It's a very useful exercise. Sometimes we are asked to simplify a circuit using only NAND gates, only NOR gates, because NAND and NOR are universal gates. Any circuit can be drawn, any circuit can be implemented using only these two types of gates, this type or that type, NAND or NOR. And as I said in IC design, Uniformity is very important. When you do a digital IC design, instead of having a jumble of gates, some 7 or 8 AND gates, another 6 or 7 OR gates, some inverters, put them all into NAND gates. One extra step there, use only 2 input gates. Then that is uniformity, the packing density of a digital size IC becomes very good, efficient. Only one type of gate is easy to manufacture, and using only one type of input, 2 input, becomes the packing density becomes very efficient. Now, I will give you a minute. Now everything is fine here, 2 input NOR, 2 input NOR, 2 input NOR, 2 input NOR, this 3 input NOR. Can you convert this into 2 input NOR? Take a minute, couple of minutes and come up. Do you understand my question? I want the final 3 input NOR gate to be made into 2 input NOR gate. Of course, you need extra gates. You cannot make a 3 input NOR gate into 2 input NOR gate without an extra gate. Do it. When somebody has done it, raise your hand. Let me see. Somebody?
NOR gates again.
Yeah, see, you make it simple, yeah, you are right, but I'm going to make it simple. Now it's a 3 input NOR gate, right? This is what it is, right? You want to call this G bar XY, right? You call it G bar XY, correct? Now, you put an inverter here right away. OR gate followed by NOR gate. I make it an OR gate temporarily, even though it has to be an OR gate finally. Now, how do you make a 3 input OR gate into 2 input OR gate? Right?
Yeah.
Now put an inverter here. Put an inverter here. Similarly, put an inverter here. Now, this has to be converted into Y bar. This becomes your G bar X. This becomes Y. Now, if this to make it as an inverter, I need an inverter, but I can go with this. I become Y bar here. That is it. As simple as that. Correct? Anybody else has a question there? Basically, you should know how to convert a 3 input gate into a 2 input gate with an extra logic.
লাইভ করছে প্রফেসরটা।
Huh? What? Say it again. Somebody said something. Yeah, you said something. Right. That's all there is to it. Okay, we will stop here this topic. To summarize what all we have seen so far in this course.
Sir, Mr. Naresh want to say something.
Naresh, say it again. Say. Mic is yours. Mr.
Yeah,
Naresh. Huh?
yeah, please. Yeah, talk something, Mr. Naresh. We can hear you.
But he doesn't know what to say. Mr. Naresh.
Yeah.
Tell me. What are you looking at, sir? Huh? ठीक है? Not happy. Naresh seems to be unhappy.
I think there's some micros. There's some. I think he can't hear us. There's some problem in the end.
Naresh.
Check your micro settings, Mr. Naresh. Check your audio level, please.
Naresh is only smiling. I cannot hear him. I can see his face and he's smiling.
Hello.
Hello. Yes. Okay. To summarize, you can convert any gate. You make first of all two input gates, everything. And or invert or and invert, whatever is given to you, convert into two input gates and change two input gate into AND or NAND or NOR, but do not put inverter unnecessarily, because inverter on one side and inverter, one output inverter and one input inverter get cancelled. So, you can save on the number of inverters, that is all there is to it. And sometimes you may have to put an extra bar, because as I said in this case D bar, G bar. So, sometimes some extra bar is required, because that inversion is required as input, and when an input inversion is required, the variable has to be changed to its bar. Anyway, to summarize what all we have seen so far in this course, we started with what is a digital signal compared to what is an analog signal, what is a discrete time signal. We talked about the advantages of using digital, because it is easy to process using computers, because we deal with numbers, and it is easy to store in memories digital signals, and once you store it, it remains intact. There is no leakage of charge as it happens in the case of a capacitor. Analog circuits, analog values is difficult to store. It has to be processed, and if there is a change in the value, you may not know that. Then we said we need an A to D converter, because all signals are analog to start with, and all signals outputs are required to be analog. So, you need an analog to digital converter as the input of the processor. Output of the processor is again digital, has to be converted to analog using D to A converter, digital to analog converter. And in between they are only taking with numbers. We are talking about dealing with numbers. All signals are represented as numbers in digital system. That is the greatest advantage because of the computers available. And the other thing is we will only deal with binary signals, zeros and ones. Any signal can take only two values, 0 or 1. 0 can be 5 volts, 0 can be 0 volts, 1 can be 5 volts, it can be 0 volts and 3.3 volts, 0 volts and 1.2 volts, whatever. Switch on, switch off. Switch on is 1, switch off is 0, like that. Now, at the same time I can increase the precision or accuracy of the signal by having more than one level. If only one level, only one switch, I can only say if the signal is present or signal is absent. But the signal has to have different values, I need to have more than one position. So, if I have two positions, I can have 0, 0, 0, 1, 1, 0, 1, 1, 4 values are possible. If you have 3 switches or 3 positions, I can have 0 to 7, 8 values and so forth. So, depending on the accuracy or the representation you want, you can have as many levels as possible, but we will only have the number of levels as required for our application. Then we talked about simple Boolean algebra, circuits, AND gates, OR gates, NOR gates, different types of gates, AND, OR, invert, NAND, NOR, exclusive OR, exclusive OR, exclusive OR, exclusive NOR, out of which we said AND, OR, invert are called fundamental gates because all combinations of digital signals can be derived using these, can be represented using these 3 gates. Other gates are called derived gates, NAND and NOR, exclusive OR, because they can be formed using NAND, they can be formed using AND OR invert. But out of which NAND and NOR are supposed to be unique because they are called universal gates. Whatever the logic function you can represent using NAND or NOR. And then we talked about truth table. Supposing you have a circuit with many gates, different signals, output is written in terms of an expression called Boolean expression. Boolean expression have only variables which are 2 values each, 0 and 1. So, we write a truth table, that means all combinations of inputs are represented and corresponding outputs are represented in a truth table. Then you get a Boolean expression. So, the circuit symbol, the Boolean expression and the truth table all are required. Once you have the Boolean expression, you can simplify it using several methods. One is the Boolean algebra, very simple identities like x plus x bar is 1, x and x bar is 0 and things like that. Or you can use a map method using corner maps, 3 variables, 4 variables, 5 variables, 6 variables I said, but it is not, it has become cumbersome. Or you can have computerized methods, reduction using computerized methods. Then we talked about different types of don't care, we talked about don't care conditions. That means a circuit will have a combination of inputs which does not occur in practice for some reason. Example is BCD. BCD has only 0 to 9, whereas BCD has 4 variables B0, B1, B2, B3. So, out of these 6 combinations corresponding to 10 to 15 do not occur. So, those are called don't care outputs because those outputs will not occur. So, those can be used to simplify the logic further. I gave you an example of that today. Then we talked about how to convert signals, circuits into NAND only, NOR only, 2 input NAND, 2 input NOR. It is very simple to translate it because we have already seen that using NAND and NOR we can have AND OR invert. So, gate for gate you can replace, but that is not efficient. You have to make sure that the inversion at the output and inversion at the input get cancelled. So, without using extra inverters we can do that. That is all we have seen. Now, we are going to switch over to actual circuits which are going to be used in digital. Things like arithmetic circuits, adders, subtractors, things like multiplexers. What is a multiplexer we will see. decoders. How do you decode a signal? Now, the only difference is these basic circuits are low level. This is called SSI, small scale integrated circuits. If you remember, we had a hierarchy. We have a digital system like a computer, microprocessor. Then it is divided into subsystems, arithmetic logic unit, memory, these are called subsystems. Then subsystems is made up of modules, adder, logic unit, counters. They in turn come as digital circuits, basic circuits, combination of AND or invert. And then you go one level down, we have not seen that level. How do you get an AND gate? Using transistors, CMOS transistors today. Earlier it was bipolar, today it is CMOS. So we have transistor level representation which we are not seeing in this course. Then we have a circuit level representation using gates. And then we have a module level representation using things like arithmetic units and all that. Then subsystem levels and then systems. Now, the very basic thing is transistors, we are not going to see that. So, what we have seen so far as the basic thing is gates. Gates are called SSI, small scale integrated circuits. All of them are ICs. What is an IC? You know now, basic made up of a single crystal silicon in which you go through a chemical process, etching and all other things. Today, lots of advances in technology, ion implantation and things like that. So, a simple gate is called a small scale integrated circuit because it is only about 10 transistors in it. If you ignore the transistor part of it, a gate is a single unit, small unit. That is why it is called a small scale circuit or small scale integrated circuit. Then you have a medium scale integrated circuit. Medium scale integrated circuit will have more than a single gate up to 10 gates. In a circuit with up to 10 gates, it is all only thumb rules, no definition, it is not a hard and fast rule. Up to 10 gates is called a small scale integrated circuits, approximately. Do not ask me what will happen if it is 11 or 9, it is an approximate number. From 10 to about 100, it is called medium scale integrated circuits. We make SSI or gates. These are multiplexers, decoders, adder, etc. Then you have LSI, large scale integrated circuit, approximately again up to 1000 gates. Not each one is a gate, it is a gate equivalent. Multiplexer is a circuit which can be reduced to gates. So, how many gates will make a multiplexer? Approximately. That decides whether MSI or SSI or LSI. So, it is a gate equivalent or transistor equivalent. So, LSI circuits are simple memory cells, ALUs, logic, all this, arithmetic logic unit and things. And then we have VLSI. VLSI has more than 1000 gate functions. It can be 10,000, it can be 100,000, it is 1 million, today is 10 million. But a lot of people say this is VLSI, extra large VLSI and things like that. We do not have all that today. It is enough if you say VLSI. All of your microprocessor is a VLSI, your Pentium processor is VLSI, your cell phone is a VLSI. All these things are VLSI. One of them may be 1000 gates, the other may be 10,000 gates, one may be 1 million gate, does not matter. So very large integrated circuits are computers, microprocessors, DSPs, etc. DSP stands for digital signal processing processor. Now, so far we have been sticking to this. We saw what gates are, how to combine them to make useful circuits. We wrote some simple word problems. Supposing you have to have a circuit which is going to detect a condition. Now we are going to move on to this level. We will spend a lot of time on this level. And also things which I have not talked about here are counters, flip-flops. We will see them separately. These are called sequential circuits. Now, MSI will have, we will not look into the gates again. We will say, we will put it as a box. Input output specific functions are specified. What are the inputs, what are the outputs? Inside there are gates. Sometimes we will see how you get that, not always. So more and more gates we put to make it MSI, LSI, VLSI, number of advantages are there. Size gets reduced. If you put more and more of these transistors or gates into one circuit, the total size, total requirement of the space is reduced. Then you have power consumption is reduced. Instead of having separate circuits and powering each of them using your 5-volt source, put them all together in one IC, give a 1 5-volt source, it is reducing much, it consumes much less power. So the advantages of it is MSI, LSI, etc. As we go here, size reduces, power consumption reduces, cost reduces, because packing is same. You make one IC and pack it together as one IC, and reliability increases because they are very closely manufactured using chemical processes. The possibility of something snapping doesn't exist. As you go up the ladder, you get size reduction, power reduction, cost, and reliability increases. Reliability increases, I think I should put it this way only. Reliability increases. So starting next lecture, we will talk about MSIs. We will look at multiplexers, we can look at adders, decoders, how to combine them, how to do a decimal addition using. We already talked about the one thing when I summarized, I forgot to tell you that we talked about codes, we talked about number systems, we talked about binary numbers, octal numbers, decimal numbers, hexadecimal, we talked about conversion of one to the other, we talked about one's complement, two's complement, we talked about how to do a subtraction using addition, using two's complement or one's complement. We also talked about codes, binary codes, gray code, ASCII code, etc. So we covered a long list of things. I think today is the 8th lecture, I think. So 8 lectures we have covered quite a bit material, and you will see in the same pace we will have a lot more to see. Okay then, see you on next Monday. If you have any questions you can ask me. Unmute them.
Okay, sir.
Any questions? Nobody has questions, as usual. Okay. No questions, I will go.